We looked at quite a bit last time, so we started to think about what if there's more than one charged object in the universe, which there definitely are. In that case, how do we account for all of their electric fields? In other words, the net electrical effect that multiple charged objects have at a certain point in space. And all we have to do is imagine that only one of those objects exists at a time, find its electric field, which is still the idea of what does it do to charges at that point in space. And we can imagine figuring that out using a test charge, pull a little charge out of our pocket, measure the force on it, divide by the size of the charge, so the answer doesn't depend on which charge we used. And that number we get, we call the electric field. And to find it for multiple charged objects, you just use vector addition to add together the individual fields to get the overall effective field. And you can start to draw pictures of that electric field if you measure it at many, many different points and connect the dots. That is the electric field lines. And you have these field lines for lots of different arrangements or distributions of charge. We looked at two like charges, two unlike charges, and then we had the individual positive and negative charge. And we started to get a sense of the geometry of the electric field around those things. So the idea was you can hold up some little charges, the white charges, at different points near these yellow charges. Speed it up a little bit so you can kind of see what they're doing. And you'll see that they tend to move, in this case, away from the left charge and towards the right charge. That's just the tendency of little positive charges in this space. But that's saying something about the space itself, the electric field those two yellow charges are creating. We can't see it right now. All we're seeing is the effect it's having on charges. But if we measure the force those charges are feeling and divide by how large they are, we can plot that number. We can plot a vector describing its direction and its size. And that is the field vectors. They tend to be away from the charge on the left and towards the charge on the right. But the plot is a little bit busy drawing it like that. So if we sort of connect those arrows, connect the dots, we get the field lines. And that really shows you the shape of the electric field, how charges would tend to move if we placed them near these two large charges. They'd move away from the one on the left and towards the one on the right. And again, this is on canvas and there's like a ton of different arrangements, so you can start to get an intuition or a feel for what it should look like in different situations. Now, some of these we don't know what they are yet, like a dielectric, we'll talk about that later, but I definitely say play around with this a little bit and it'll help you get a better feel for what an electric field is. Now that we've done that, we're just going to make sure the rules for field lines make sense. So these few rules down here, by looking at an example. So this is someone attempting to sketch field lines, and I guess you asked 4 different people, got 4 different answers. Only one of them is right. So we're going to run through them and try and figure out what's wrong with each one. Let's look at case A. What's wrong with it?
The field lines overlap.
Yeah, they cross right here. Why is that not okay?
Well, they can't really like share electrons. They just kind of move around, right?
It's not about electrons. There's nothing actually necessarily present at that point, but you can imagine putting something there to see what would happen to it. So these aren't atoms necessarily either. That's not for sure what's going on. It's just these are amounts of charge in space. It could be atoms, but it could be anything that's charged. So if I put something right here at this black dot, I put a little positive charge there, which way is it going to go?
Toward the negative charge.
Which one?
The field would point in 2 directions at once.
Yeah, isn't that a problem?
Yes.
Yeah, that's what we're getting at, is the field kind of doesn't know which way it points at that location if 2 different lines cross. And so it's almost like it's saying, I might send a little charge you put there this way. I also might send it this way. Just depends how I'm feeling that day. Everywhere else, there is a definite direction that charge would go. So that's the problem, is it's saying something about like, I don't know what happens there. But then how would you have a field line there in the first place if you don't know? Okay, for part B, do you see any problems with that one?
One of the negatives only has one part side of its field.
What's the problem with that?
Hmm.
You're comparing this versus this, right? And saying they should have the
Yes.
same number of lines. So you're right. I'm not disagreeing with that. I'm just asking, why do we need to make sure that equal amounts of charge get equal amounts of lines?
Why wouldn't they?
Well, it would mean that the field strength is totally different here than it is over here, because we have 2 lines right here versus only 1 right here, and the spacing of the lines tells us about the strength of the electric field. And that's the
But I mean,
problem.
they're the same charge, the same value, right?
Right, exactly. This is the problem. You've found the problem is that if they are equal amounts of charge, the fields they create near themselves should be equal, should be the same as each other. So the field over here should look very similar to the field over here. But that field's reflected in the spacing of lines. If we don't have an equal amount of lines, there's no way the field can be the same. So that is the issue. So the lines are not proportional to the charge. And in fact, there's more than that wrong. We see 8 lines leave the positive 4 charge. 1/4 of those should go to one of the negative Qs because it's 1/4 as much charge. We see 2 enter this one. We saw only 1 enter this one, so that's the first problem we notice. We really should have this right here. But there's too many entering the negative 2Q. It should have 4 enter it because it's half as much charge as the 4Q. But 5 actually enter. That's what we actually see there. 5 enter. All right, so B is out. What about C? We see any issues with C?
I think C looks good.
It's good.
Okay, then let's jump over to D and just say what's wrong with it real fast. So what's the issue with part D?
I'm assuming it's because the field lines are straight. They
Yeah.
should kind of be curved.
Why should they be curved? What does the spacing of the lines tell you about?
It tells you where the field is going.
Where it's going, but also, like, what is the difference here versus over here? The spacing of the lines tells you about the what of the electric field.
The size of it?
Yeah, or the strength of it.
Mm.
So wouldn't we expect that if we're not right by one charge or the other, the field should be a little bit weaker? We're farther away from either one of them. So what we're seeing over here, this is like you call it a uniform field, equal strength everywhere. We do not expect to see that between 2 charges because it should get weaker when we move far away from them both in the middle. So that is the problem. The field should get weaker, meaning spread out further, farther, again, I can never remember, from charges. C checks those boxes. We also see that 2 lines enter right here, 2 enter right here, 4 enter right here, and that's good. That's a total of 8 entering charges because 8 left. The lines are proportional to the amount of charge. So got no crossing. We've got that the lines leave positive and enter negative. We've got that the lines are proportional to charges, and we've got that the line spacing reflects the field strength. So that is a pretty good sketch. Okay, we can come back to something I said at the beginning of the class about how without electricity, our hearts would not beat, and in fact, any muscle would not contract. It's a similar process for most muscles, but the heart has a few special things going on. The main thing it has that the other muscles don't have, it has a rhythmic contraction. It regularly contracts and expands. We don't need to think about it or make something happen to contract and expand it. We're going to very roughly explain how that works here. There's a lot going on inside the heart, and it's a rabbit hole you could dive down for a couple days. The other thing is, my expertise in biology is 9th grade. So I'm only going to be able to tell you so much, but I'll tell you what I can here about how this works. So the thing that causes this rhythmic contraction, the thing that's different from other parts of the body, is this thing right here. It's called the sinoatrial node. Inside of it, it has something that they call pacemaker cells because their whole job in life is to regulate the heartbeat. And they do it by starting what's called a depolarization wave. So the rough idea, which I wouldn't even recommend drawing what I'm about to draw, is just to help me verbalize this. The rough idea is that inside of your heart cells, you've got mostly negative charge on the inside in the resting state of the heart cell. The outside is mostly positively charged. What the depolarization wave does, again, roughly, is exchanges ions, so things like sodium and potassium and calcium, in order to reverse the polarity here. To make this positive, negative, positive, negative, positive, negative, positive, negative. So it reverses what charges where by shifting ions around through what are called voltage-gated ion channels. They're just like little connectors between the inside and outside. What that does, it triggers the cell to contract. How it does that, that's one of those things that's a rabbit hole. But that's what ultimately happens is the cell contracts when that depolarization wave passes. And so what the sinoatrial node does is it starts this wave off, and then that wave travels through the heart cells in the atrium, and eventually you get over to this atrioventricular node, or AV node. And while the wave is spreading to the other atrium, this thing is making it so there's a delay that happens. And the delay is how long it takes for the wave to travel down to the bottom of the heart, to the ventricles. The reason you need that delay is what's up in your atria right now? What's pooling in them at this moment?
Blood.
Blood. So you've got blood pooled up in the atria. This depolarization wave that's passing by, which I'll sketch in an arrow to say this is the direction it's going, what that contraction is doing is squeezing the atria, and it's going to take that blood and push it down into the ventricles. So that's your blood. The reason you need the delay in the depolarization wave as it heads down towards the bottom of the heart is so that the blood can fill up the ventricles before they get squeezed. But once the blood is down here and this delay has happened in the depolarization wave, it does start to spread to both sides of the bottom of the ventricles. And that's sort of like you're squeezing the bottom of a blood bag, and it takes that blood and pushes it out to the rest of your body. Okay, so the process is the sinoatrial node triggers things. It sends this depolarization wave down through the atria, and that squeezes the blood out of the atria into the ventricles. At the same time, the atrioventricular node takes that depolarization wave and delays it, makes it go down to the bottom of the ventricles, and eventually squeezes them to take that pooled blood out to the rest of your body. And while all of this is going on, it's sort of like a domino thing where all of this depolarization flips back, also through diffusion of ions through those channels, until it reaches its normal resting state again. And that's sort of following right behind the depolarization wave. It's called a repolarization wave, to reset everything. And I don't want to sketch it in because this is already enough of a mess of a picture. I'll come over here and show a better animation of that. So there's the sinoatrial node firing, squeezing the atria. There's the blood pooling down, and this signal to the atrioventricular node. It delays the signal. It makes it take longer to pass down to the bottom of the ventricles, which you'll see here in a second through these bundle of his, an atrioventricular bundle. But now you see the blood is down in the ventricles. It's pooled in there. And now this signal is going to head to the bottom of the ventricles and then spread out to the left and right hand side to squeeze the ventricles. This stuff on the left and right they call the Purkinje fibers. That bottom of the heart part is what squeezes the blood out, sends it to the rest of the body. And we'll talk about how that relates to EKGs a little bit later in the semester. Slightly different visualization where you can actually see a better view of the pathways is this, and it's faster, so you can see the whole thing sort of going on. Okay, so what does this have to do with electric fields? Well, positive and negative charge create electric fields, and those fields point away from positive towards negative. You can track where that depolarization wave is in the heart by seeing where you've got a concentration of positive charge and negative charge. I'm going to go now from the perspective of what's outside of the cells. They're initially positive and then flip negative. The depolarization wave is sort of that frontier between the outside of the cells being positive and then being negative. And you can see that in this view. So you can see our frontier of positive, that's where the depolarization wave has not reached yet. Negative is where it's already passed. And that yellow arrow is the electric field that's being created. It's a dipole-like electric field being created by that frontier. And this is where the blood is going to be pooling down from the atria into the ventricles. Now that electric field and the depolarization wave has reached down to the bundle of His, as they called it. And then it continues propagating down towards the bottom of the heart and through those Purkinje fibers off to the side, and spreading and spreading and spreading. And then we reach back to that restart. We get back to that original picture. So this is just a loop of it. You can actually track the health of the heart by tracking that vector showing which way the electric dipole is oriented inside of your heart. That's this picture right here, but you don't have this picture. I've had to sort of mesh it in from an earlier version of these notes. But this is particularly when the depolarization wave reaches the bottom of your heart. So it's just zooming in on that part. If you track the orientation of that dipole, meaning where's their positive charge concentrated, where's their negative, and how much, that's the size of this vector, it rotates as your heart beats. So this is earlier in the heartbeat, a little bit later, a little bit later, a little bit later. And ideally, it just follows that same path over and over and over very regularly. The mean electrical axis is what you get if you average all of those vectors. On average, which way does that dipole face in your heart? And the direction that points says something about the health of your heart. For instance, things like hypertrophy of the heart, that something's a little bit too large, that might mean that the depolarization wave spends a little bit too much time there, and it shifts that mean electrical axis towards that part of the heart. So it's a diagnostic tool. You more often see EKGs, and again, we'll talk about those later, electrocardiograms, to tell you about this, but there's also something called a VCG, a vector cardiogram, and it's actually tracking specifically this vector and saying, is it in the right spot throughout the heartbeat cycle, or is it a little bit offset, and what does that say about the heart? So again, a lot going on inside the heart to fully explain what's going on there, but roughly you can think of your heart as a dipole. So almost imagine like a baton connecting a negative and positive, and that dipole is just spinning around and around and around. Sometimes it gets stronger, sometimes it gets weaker, but that's your heart. It's almost like a little generator inside your body, and that's just spinning and spinning and spinning, and that's the depolarization wave traveling throughout your heart, down towards the bottom and up towards the right-hand side, up towards your left-hand side. EKGs are reading this, they're just doing it in a slightly different way. They do it using something called potential, which we will get to in the next chapter. Okay, well, if electric fields are an abstract concept, Gauss's law is a very abstract concept. So I'm going to do my best to get the idea across, but it is kind of tough the first dozen, 100, maybe 1,000 times you see it. Honestly, when I reteach the course, I always have to read back over some stuff for Gauss's law to make sure it makes sense to me. I'm going to start by giving you this idea of putting a bag around charges. Imagine you have a plastic grocery bag, like a Kroger bag or something, and you just take those two charges and you bundle them up. It's like you're catching them with that bag. You seal the bag up tight, now it's completely closed. the electric field can still pass through that bag. So it can poke into it, can poke out of it. The charges are stuck inside the bag. The question is, can I, just by looking at what's poking out of the bag, determine what's inside the bag? So maybe someone else caught some charges. They brought them to my house and said, what do you think's in here? I study the electric field lines that are poking out and poking into the bag on the outside, and I say, I think I might be able to tell you what kind of charge is inside that bag. Or vice versa. If I know the charge inside the bag, can I figure out something about the field on the surface of the bag? That's the statement being made by Gauss's law. We use the fancy term Gaussian surface, but it really is just a bag. An imaginary bag enclosing a region of space. And it's imaginary because we are just imagining enveloping these charges in this. They don't have to actually be sitting in anything. It's not a physical, tangible plastic bag or anything like that. So to be more specific, let's see if we can see a more numerical relationship between the number of field lines and the charge inside the bag. So look at surface 1, this one on the left-hand side. How many field lines poke out of that bag?
Okay.
Let's see, I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And they do all poke out, yes. Do you see any lines poking in?
No.
Nope. So the net number of lines leaving is you take the number leaving, you subtract off the number that are entering the bag. And you can think of that as any lines that enter cancel out a line that leaves. So you just want to know, in effect, the net number that have left the bag. But in this case, that would also be 10. How much charge is inside that bag?
Just one positive.
Yeah, it's that plus Q right there. So remember, Q is just it's a name for charge. It's a variable. It can mean any number, 2, 10, a million, whatever. But it's a positive amount of charge. Let's move on to surface 2. How many lines leave that bag?
0.
0. How many enter it?
20.
All right, I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I agree with you, 20 enter. So the net number leaving 0 minus 20, negative 20, which we can interpret as just 20 enter instead of leaving. So negative 20, or this just means the net number actually enters the bag. How much charge is inside that bag?
2 negatives.
Yeah, minus 2Q. Now let's ask kind of the reverse question. How much charge is inside bag 3?
0.
Yeah, there's
0.
no charge inside bag 3. So without even counting, what is the net number of field lines that leaves that bag, you think?
0.
0. Are you seeing the pattern? When there's 10 lines leaving, it's plus Q. When there's negative 20, it's a minus, and it's twice as much. When there's 0 leaving, there's 0 charge enclosed, or vice versa. And, if you're not convinced on that one, you can go back and count them. You can say, well, 1, 2, 3, 4, 5 enter. And 1, 2, 3, 4, 5 leave. So yeah, just as many enter as leave. The net number leaving is 0. So we're mostly looking at the last 2 columns and saying the net number leaving and the charge enclosed are proportional, meaning one is a multiple of the other. All right, now we look at surface 4. That's one where counting the lines actually becomes a little bit of a pain, but I don't need to. How much charge is inside of bag 4? Well, we've got this one and this one inside of that bag, right?
So is that going to be -1?
Yeah, -1 units, however many Q is, of charge. So minus Q. So just from that, what is the net number of field lines leaving that bag?
-10.
-10. I just did that without counting. So I have developed a tool that connects how much charge is inside the bag to how many field lines poke out of or into the bag. And again, if you're not convinced, we can go through and count. The number leaving surface 4, I see 1, 2, 3. I keep going around. A lot of these are entering. 4, 5. So I see 5 lines leave bag 4. And then entering, I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So 15 enter the bag. 5 minus 15 is negative 10. So that's the observation that Gauss made, is if I enclose my charges in an imaginary bag, I wrap them up in it, and I just count how many field lines poke out of that bag in the net, I know something about how much charge is inside, or vice versa. If I know about the charge inside, I immediately know something about how many lines poke out or into the bag. The net number of field lines leaving a Gaussian surface, which again, is just a fancy name for a bag, is proportional to the charge inside the bag. And even more importantly, knowing something about the amount of field lines leaving or entering is telling us something about the electric field on the surface of the bag, because the closer the lines are, the more will count up, and so the stronger the electric field. This is really a statement about the connection between electric fields and the charges that create them. Gauss's law gives us a connection directly between those two things, even for really complicated distributions of charge. I want to give you another way to think about it. So you remember we said that we can think of positive charges as fountains of field lines and negative charges as drains. This would be like take a bag and put it over a fire hydrant, but then you suddenly see water spewing out of it. You have a guess what's inside that bag. So what's going on the surface of the bag, the water spewing out, tells you something about what's inside the bag, the fire hydrant. Likewise, if it's flooding out, but you see someone who has a bag over something and lots of water is flowing in to that bag, what do you think's inside the bag?
If it's flowing in, that would be like a drain, so it would be negative, right?
Yeah, it's a drain. That's all it is. That's what's inside the bag. So, knowing what's going on the surface of the bag, water's flowing in, tells you something about what's inside the bag, a drain versus a fire hydrant. The amount of water, which I'm sort of equating to the electric field, spraying out of a bag tells you what's inside the bag. And that's going to be, in the water version of this, a fountain or fire hydrant or drain, or could be neither. If you see just as much water flowing into the bag as flowing out, it's not really catching anything. Water's just passing on through it. So there must be no net water source enclosed, similar to bag 3 up here. You're catching just as much water as spraying out. There's probably not anything in there spraying out water or draining that water. And that's analogous to charge. So that's the idea of Gauss's law. Does anyone want me to go back through that? I know there's the recording, but seemed like there was some confusion. So I want to clarify if I can.
Could you go through it one more time, please?
Yeah. So what I was doing up here was mostly just noticing a pattern. And the pattern was that if I count up how many lines poke out of the bag and then poke into the bag and then add those up to find the total number poking out, the net number poking out, That's directly related to how much charge is inside the bag I'm picking to look at. So when I looked at bag 1, or surface 1, I found that 10 lines left it, and positive Q charge was inside it. But when I looked at a bag that had twice as many lines and they were all sticking in, I found a charge inside that bag that was twice as big and negative. When I looked at a bag that wasn't catching any net number of field lines, there were just as many entering as leaving it, I didn't find any charge inside that bag. And then when I looked in a bag that had a net number of 10 lines entering it, it had a negative amount of charge inside and the exact same amount as when I had positive 10 leaving. It's just now they're opposite signs to each other. So the idea is just by counting how many lines poke into or out of that bag, any bag you want to draw, it's not just these 4 that I picked, you can draw a new one for yourself and check this. But any bag that I pick, the number of lines that poke out of it is related to what's inside it. That's Gauss's law. And then the water analogy was just to give it something more everyday. Instead of thinking about charges, thinking about faucets or fountains or whatever is a source of water that sprays out, whatever most conveys that to you, versus drains or sinks. A positive charge is like a faucet, a negative charge is like a drain, because positive charges spray out lines, negative charges suck them in. So, if you're walking along the street outside and you see a guy and he's holding this bag up over something and you see tons of water spraying out of that bag, you don't think there's a giraffe in there. You don't think there's a clown. You think there's something that sprays water. If he is holding that bag over something and you're seeing lots of water go into it and not come back out, you're not thinking it's something random. It's something that drains water. So it's sort of a magic trick in and of itself that you can predict what's inside the bag just by knowing what's going on its surface. That's the magic of Gauss's law. That's what it does for us. Now, how it does it for us, that's the not so fun part, because we have to turn this statement in the box into something we can compute with. These counting bits up here, it gives us the rough idea, but we need something very concrete to actually calculate how strong electric fields are or how much charge is present. And so that's our next job, is to turn that boxed statement into an equation. So the first task is coming up with a mathematical way to count how many field lines poke into or out of a surface. And if we look at a surface like this, so this is our Gaussian surface. This is just another one in another possible electric field. That's our bag. It's kind of hard to imagine or think about how many lines are poking into and out of the entire bag at once. Instead, we could simplify down to just one tiny piece of the bag. You cut out a little rectangle out of your plastic bag with some scissors and just focus on how many field lines are poking through that. And that's what I'm doing by looking at just this right here. This is a patch of the full bag. And so my job now is a little bit easier. It's how many lines are going to pass through that patch? And my question is, what's that going to depend on? What would change how many lines actually poke through that patch?
Whether it's positive or negative.
Positive or negative will change whether it pokes in or out. I do agree with that. But how many is what I'm concerned with right now. I'm asking what's going to make it so more lines poke through? What's going to make the picture go from what it is right now to a picture where I'm seeing lots of lines passing through?
The surface area?
Yes, yeah, that's a good one. So if I shrunk down the patch, it's not going to catch as many field lines. If I make it much larger, it'll catch more than it did before. So it does depend on the area. A larger patch will catch more lines. What else? So that's the bag changes a little bit. You stretch it out and it's catching more of those lines through that little patch. But what would increase the number of lines themselves?
A higher charge.
More charge, or a little bit more directly, a stronger electric field. Because remember, closer lines correspond to a stronger field. You're packing more into that patch. So a field strength. That will matter. And the reason I'm worrying about the field instead of the charge is because remember, my goal is to count up how much field passes through this surface, and then use that to figure out something about how much charge is inside. If I'm using the amount of charge inside to try and count this, I already know the answer to what I'm looking for. I have to here use observations I can only make on the surface of the bag, and I can't see what charge is inside it just by looking at its surface. Okay, so makes field lines denser, packs more into that patch. And one more. So here's the current patch I'm looking at. What if I laid that patch flat, but the electric field was still in the same direction? Is that field line poking through the patch now?
No.
No.
No, it's just grazing its surface. It's skating across it. It's not poking in or out. So the orientation of the patch matters. And then there's the question of what if we're sort of somewhere in between? Then what? Would you say it's poking through or not poking through?
Is.
It is, but not as much as this one, right? So you have to shift your thinking from this binary, is it poking or not, to it's very much poking or it's very much not. It's a spectrum of those possibilities. Your in between is poking all the way through or it's just grazing the surface. And the way we do that is think about how much of that electric field vector is sticking out of the patch versus how much of it is grazing. So I imagine the pieces of this electric field, the components. One of them actually does stick completely out of the patch. There's this other component of that electric field vector, though, that grazes the patch. I'm interested in this one, because it's the part that actually pokes through. This part just grazes the surface. And in order to figure out how much of the electric field vector that part is, I need an angle. So I'm going to measure this angle right here. Call that my angle theta. It's the angle between the electric field vector, and then we call this the normal direction or perpendicular direction. It's just saying out of the patch. It's the outward direction. So the part we want is the part that points along that normal direction. It would be E times what? Cosine or sine of theta?
If you said opposite,
It's adjacent, right? It's adjacent to that angle, so use cosine. So if I can get better alignment, meaning the right value of theta between that patch, that normal direction, and the electric field, then I will catch more field lines. So think of it as a net. You're going to catch the most, I don't know, butterflies or whatever, if you actually orient the net to where they're flying into it rather than flying along it. Only the part of E along the normal direction. So E cosine theta actually pokes through. And we're going to use those three things, and this is the last part I'll say, to construct this thing that counts for us how many field lines pass through that little patch. This thing right here is our symbol for how many lines, number of lines, passing through that patch. It's going to depend on how densely packed are the lines, which is reflected in the electric field strength. The closer the lines, the stronger the electric field. It's also going to depend on, do those lines actually poke through the surface or not? And finally, it's going to depend on how big the patch is that's catching those lines. And we call this thing the electric flux. But just think of that as another way of saying number of field lines that passes through. And last thing is just the units. Electric field has units of newtons per coulomb. Area has units of square meters. So it's Newton meter squared per coulomb. This is one of those things where having lots of props definitely helps, and I don't have recordings of that, unfortunately, and they're all on campus. So if we're back in person on Wednesday, then hopefully I can show you in a little bit more tangible way. But still, if you haven't looked back over the electric field stuff from the previous recordings, I would strongly recommend it because it needs to feel very comfortable by the time we're getting to this, because it's just yet another layer we're adding on to it. If you want to practice this more, I would recommend drawing a new bag. It can be whatever you want, any wild shape, and still do this counting procedure and see that no matter what you do, the net number of field lines leaving that bag is always proportional to the charge inside the bag that you drew. It's surprising the first few times you do it because you're going to try and find a bag where it doesn't work, but you can't unless you do something a little bit squirrely with you're only half enclosing the charge. But you can't do that because then the charge isn't inside the bag. So only bags that are actually enclosing charge, but then this does work. Any questions?
Can you go back down to the yes that the normal
Mhm.
line, is it the hypotenuse or is it the adjacent line?
Let me kind of resketch this real fast. The normal is just the nose of that patch. Like, think of your nose on your face. It sort of sticks out from the plane of your face and says, that's the outward direction, out away. That's the role of the normal, is just to say, what is outward? Which direction is it? As far as the triangle goes, the electric field is actually the hypotenuse. And then this is E cosine theta. This is E sine theta. The only reason I drew it over here was because then it's much clearer that it's grazing the surface. It's easier to see that it's E sine theta if I draw it over here. So it's a losing battle. I'd have to draw it both ways, which I guess I just did, for you to kind of see both pieces, that it's grazing and that it's E sine theta. Does that answer your question?
Yes. So the normal line basically just tells you which like direction it's going.
It tells you which way the patch is facing. The electric field
Okay,
can
okay.
poke in all sorts of different directions. This doesn't change unless the patch is facing a different direction.
Okay, I see.
I will see y'all, I hope to God, in person on Wednesday, and have a good day.